Okay, welcome everybody. This is our final AGN seminar of the semester. I know everybody who's at universities is probably exhausted and worn out right now. So thank you so much for taking some time to join us today because we really have a very exciting talk lined up. And so we're very happy today to welcome Enrique Lopez Rodriguez. I met Enrique a couple years ago when he came and visited at Georgia State University. And we had a great time getting to know each other. Enrique is originally from the Canary Islands, so that's a wonderful place to develop an interest in astronomy at a young age. He moved to the US for his PhD, which he worked on at the University of Florida, while also spending some time at Utrecht in the Netherlands. He then moved to UT Austin, where he worked in a couple different positions, and then was working at Sophia in a couple different positions as well, while holding a JSPS fellow position at the National Astronomical Observatory of Japan. So Enrique is one of those very international people
one
in our
question.
field. Yes. No. Okay. So let's see here. So Enrique is now at the Kavli Institute for Particle Astrophysics and Cosmology, and he's going to tell us today about radio loudness in AGN using far infrared polarimetry. So thank you, Enrique, and please take it away.
Excellent. Well, thank you, Misty, and the rest of the organizers to make this series of AGN talks so nice and awesome topics for the past year or so. So I've been enjoying this a lot. So today I'm going to talk about magnetic fields. I know when the people hear magnetic fields, just like close their minds and then walk away, but please keep stay focused for a few minutes, and I swear it's going to be worth it to learn a little bit about how AGNs work in terms of MHD dynamics. So we know that AGNs are powered by accretion onto a supermassive black hole. So we have, since the past few years, these beautiful images by the Event Horizon Telescope here on the left. I will show the first images at 2 millimeter wavelength of the emission are surrounding the event horizon, around the event horizon, but also you have these streamlines on top that show you that this accretion of matter is also dynamically dominated by magnetic fields. So these magnetic fields are dynamically important and are one of the main components that create jets and the outflow formation and accretion onto supermassive black hole. So what we have is the accretion in the central AGN is in the central black hole. Maybe like this magnetically rested accretion disk, for example. Basically, what you have is dominant toroidal B field that advect B fields into the event horizon. You have a accumulation of B fields and create a vertical B field that create the jets and allows the conservation of angular momentum and the movement of angular momentum going outwards. So this is the central event horizon. Well, alternatively, you have the new theory by Noemi, Globus, and Roger Blanford that say that it's no arrestic and it's not like a matte disk. So what you have is some kind of like an ergosphere-free fall of matter surrounding a highly magnetized environment in the central 50 micro arc seconds. So if you go a little bit farther away from it, you have this accretion disk. So basically, the accretion disk is the transfer of matter going into the supermassive black hole that has more or less a distance of subparsec scale that are mainly divided, divided in the outer layers by the sublimation radius of the dust. So at least what we know is like that vector B fields are requiring all models to explain the launching of the jet and the creation flow, and also the creation of the winds that we see at large scales. So from the central parsec of the AGN, I'm gonna go and move. I'm gonna do a zoom out and then focus on the host galaxy of the AGN. So the host galaxy at kiloparsec scale, we have seen in the past several years that these host galaxies have large scale order spiral B fields. So here I show the far infrared polarization observation with Sophia at 89 microns of Centaurus A, radio loud AGN, and 1068 radio quiet AGN. So we have in Centaurus A, so it's the remnant of a merger galaxy or a merger between elliptical galaxy and H-on spiral galaxy. The streamlines that you see on top is the orientation of the magnetic field that you see more or less follow the edge on spiral galaxy, but you have some kind of like angular dispersion between beam to beam, and that is produced, that is due to the turbulent dynamo. So basically, the definition of dynamo is the transfer of kinetic energy into magnetic energy. So whenever you have some turbulence due to, in this case, galaxy formation, mergers, supernova explosions, you have an injection of kinetic energy, and that kinetic energy moves from large scale to small scales until you have some until you get a scale where the viscosity dominates, and then at that level, what happens is that you have electromagnetic induction. So then you create a magnetic field, you generate a magnetic field by viscosity of ionized plasma. So then actually it's very interesting that the same mechanism that's dissipating the energy is also the mechanism that amplify the B fields. So at a level, so when you have these merger galaxies, you may have a pre-merger B field. For example, that I show here in 1068, let's imagine that you have this spiral galaxy with an early type, very well organized B field, but the merger itself, it creates this turbulence and then amplify the B field to have a higher magnetic field strengths. So what you have here is like what we see from, at least from the galaxy, from our galaxy, is that the B fields are, the turbulent B field component is more or less in close equipartition from energetically speaking to the turbulent kinetic energy in the ISM. So at that level, what happens is that the B fields are dynamically important in the processes of gas flows. That means that you have and the star formation can be quenched if you have a strong B field, and also the formation of molecular cloud. That means fragmentation of the clouds across the starbars, the spiral arms can be also affected by B fields if you have a very strong B field regime. So this is at 4 kiloparsec scales. So if we move inwards, I'm still only focused on host galaxies that has AGNs. So if we move a little bit and zoom in, so in this case, we have 1068, 1097. So you have a spiral galaxy with a bar, and the center you have a spiral starburst ring at around 1 kiloparsec and AGN in the center. So this galaxy have basically everything you want to study for. So you have the bar galaxy creates non-asymmetric velocity flow. So the bar basically what it does is stretch and shear and compress the B field. And if you look at the two edges, basically what you have is two velocity components moving in opposite direction, and that collapse in the what that encounters each other in the center of the galaxy. So then you have to dissipate the energy and produce these spiral B fields in the central 1 kiloparsec of the galaxy. So here what I show is the color scale is the H-alpha emission. So you have the star formation, so it's a proxy for the star formation regions. The yellow lines that you see a little bit there, those are the B field from the far infrared emission. And you see the far infrared B field is constant, has no spiral component. So that's because it's also this B field is in the outer skirts of the starburst ring. So that's where you have the shock of these two B field components going into the starburst ring. The lines, the black lines that are moving, those are the B field orientation and direction or observed with the radio polarization. So here what you have is far infrared trace dust thermal emission from magnetically aligned dust grains in the plane of the galaxy, co-spatial with the star-forming regions and the molecular emission. Then the radio polarization trace the B field by synchrotron emission, non-thermal, from diffuse and warm ISM. So then what you have is perhaps what you're seeing is an extraplanar B field in the outer part of in the upper part of the starburst ring that is moving, that is allowing the warm gas to going into the central AGN and allowing the inflow of matter from kiloparsec scale to hundreds of parsec scale in the center of the galaxy. So some kind of like a feeding of matter into the black hole from the whole galaxy. So here what you have is just the full multi-scale B fields from kiloparsec scales all the way to the central black hole, but we have a missing piece. And the missing piece is the AGN Tori. So this AGN Tori, how I interpret it is the interface between the accretion flow into the AGN and also the outflows from the AGN itself. So it's kind of like the inflow from the host, from the kiloparsec scale into the subparsec scale, and also the region where you have MHD disk, MHD outflow going outwards due to the accretion process in the center. The problem here is that we have all these idea of the B fields at large scale, small scales, but we don't know anything about the magnetic field orientation, strength, and what the physical mechanism that produce, generate, and conserve the B field in the AGN Tori. So it's always being HD or static. Yeah, I mean, basically the people are fitting static clumpy torus or two-phase torus or a torus with a wing that is static, is not dynamic, and only take into account radiative transfer, and also or HD is never the B field, but we know that B fields are important in large scale and small scales. So what I want to show now is the empirical measurements of the B field orientation strength and the physical mechanism from creating this one from several observations that we have done in the past few years. So I think they're going to start with the ALMA parametric observations. This is because this is the first and only observation that actually resolve the AGN torus in using dust polarization continuum observations as a scale of 4 parsec here. So what we did was band 7 of 860 micron dust polarization continuum with a resolution of 0.07 arcsecond, which correspond to 4 parsec. And here on the left, what I show is the total flux. This is the thermal emission produced by dust. And here what I show, so this is basically the synchronuclear disk that is very well known in total intensity and continuum. So the cross here in the center is the position of the AGN. So here in the north, you have this bright spot, and this is where the jet collide with a giant molecular cloud, and then switch from north to south direction to 45 degrees, which is what I show here. So you have the core, you have this region here, that is the collision between the jet and the jet molecular cloud, and then change of direction of 45 degrees in this direction. So, and the Y contours is the total intensity. So if we go to the right, so what I'm gonna show is the Y contour is total intensity, but the color scale is the polarized flux. So this is basically like how much flux is polarized by magnetically aligned grains produce a thermal emission. So I'm gonna zoom in this area, but this is like basically 120 parsec by 60 parsec. So if we zoom in here, so in the 20 by 20 parsec, basically what you have is a unpolarized core, and you have this east region and west region of the torus to be polarized. This is the torus seen in molecular gas, in this case HCN, but this is the typical orientation of the molecular torus seen in 1068 in CO, CN, HCN, and different molecular lines. So what you have here is like the core is unpolarized, and the eastern part and the western part of the torus is polarized. Maybe we can talk about this north area. I don't know exactly what is going on. I think it's synchrotron emission, or that's polarization, but not by magnetic alignment grains, but by mechanical alignment, because you have a very strong radiation pressure due to the jet that actually aligns the big field mechanically and not magnetically. But we haven't done that study yet, but I only focus on the core in this case. So what are the properties of these torus? What we did is average of the radial profile in this box, which corresponds to the box of the molecular torus, and then estimate the flux density on the left, the degree of polarization in the center, and the position angle of polarization on the right. Basically, what you have is like the outer region of the torus are polarized, which are the eastern and the west region, at 2 to 3% polarization. The big field orientation, in this case, is parallel to the equatorial axis of the torus. Basically, what you have is the big field is parallel to the long axis of the torus. In this case, it's in this direction. And the core itself is unpolarized, right at the center of where you have the AGN and the jet. So what we did was a synthetic observation just to try to explain this from MHD point of view. So what we did was assume a toroidal magnetic field, just for simplicity at this point, maybe a spiral or maybe some 3D structure, but we don't have enough angular resolution to resolve it. So this toroidal field, we incline in the lateral side and we tilt it. We assume homogeneous grain alignment, so every single das grain is aligned at this point. I mean, can be some efficiency or no, but it's not we don't have enough multi-wavelength coverage to study that. And then what we did was create mock stocks IQU, basically the parameters that give you the polarization, the polarization degree and flux, and using the Clampitorus models by Nenkova et al. In 2009. So we published these images of the Clampitorus in Nikuta 2000 A and B. Basically, it's a radiative transfer model of the dust emission using SCD from 1 to 800 microns. And here I show the stocks IQU in full resolution. And this is the polarized flux, as you will see, you resolve it with infinite resolution. So we use this model and create some synthetic observation using CASA, using exactly the same observation conditions as we did with 1068. And this is what it should look like. So what you have is an unresolved core in total intensity, and you have in the polarized flux, you have a zero polarization in the center, and you have a high polarization in the left and the right. So we did the same cuts radio profile cuts. And in this case, what I show is the dashed line show the model at the same angular resolution, same observing conditions as 1068, but using the mock observation, and you see the same trend in total intensity. You see the same trend in the degree of polarization. You have a unpolarized core and polarized east side and west side, and the position angle of polarization in this case is parallel to the long axis of the equatorial plane of the torus. So what do we learn from this? So first, again, so the outer region of the torus are polarized. Why? So if we use the velocity dispersion of the HCN CO emission, it actually what happened is that you have a lower velocity dispersion in the east side than the west side of the torus. So lower velocity dispersion, that means that you have lower turbulence. So that allows to create a larger scale order B field. So if you have a lot of dispersion along the layer side, so then you may have a tangle B fields, or the B fields along the layer side will cancel out. Or you have a lot of loops of B fields within the beam, and then when you add a lot of loops, so you basically cancel out all the polarization. And that's the reason why you have a lower polarization in the west side than the east side, where you have a less turbulent B field in the east side than the west. So also what happened is that in the outer region of the torus, you have a low optical depth. So the lower optical depth amplify the degree of polarization. So basically what you have in the center, you have a self-absorbed emission, is because you have a lot of optical, so you have a lot of column density around the outside that creates a lot of tangle B field that cancel out. Basically what you have, it may be polarized, but then the same dust grain that polarized, you have another layer of dust grain that absorb it, and then you have exponential decrease of the polarized emission as a function of the distance along the layer side. So what we learned also, like the B field is parallel to the equatorial axis. Actually, we can constrain the inclination of the torus better than you do with ACD. And we have the inclination of the torus to be almost H-on. So that's the reason, because you have a vector quantity. And the vector quantity depends on the orientation along the layer side. In order to explain a B field that is almost parallel to the long axis of the equatorial plane, you need to have inclination larger than 80 degrees. So, and if you do with ACD, I think the ACD gives you that you need to be inclination larger than 70 or 80, something like that. We actually say that it has to be H-on in order to explain the degree of polarization from the vector components of the B field. And the most interesting thing is because we resolve it, we can use the east region of the torus to estimate the magnetic field strength. So we use a modified version of the Davis-Stern-Fermi method that gives you the estimation of the magnetic field strength on the plane of the sky. And that gives you a B field strength of around 0.7 milligauss. It's always a factor 2 or 3. This technique is not good. Doesn't really matter how many vectors you have here. You always have a factor like 2 or 3 independently there. And the interesting thing here is that this ratio between the turbulent and order B field. So this is interesting for the energetic balance that we'll talk a little bit later. So this is telling you that the order B field is dominating the B field energy in the magnetic energy in the torus. So in this case, what you have is like the constant large scale, which is toroidal B field, is dynamically important at parsec scale. When I say dynamically important, because you can estimate the beta plasma parameter, which is giving you the ratio between the gas pressure and the magnetic pressure. So if this beta parameter is Larger than 1, that means that you're dominated by gas thermal pressures. And it is smaller than 1, so you're dominated by B fields, by energetic B fields. So in this case, you have beta plasma parameter of 10 to the minus 3, more or less. So you basically are dominated by B fields, by toroidal B field in scales of 3 to, what I say here, 3 to 8 per sec. So here what you have now is start creating a picture of connection between the large scale B field to the smaller scales. At least for radio quiet AGN. You see that a radio for radio quiet AGN, that was for 1068. So it's the only one, is the less prototypical AGN ever. So for sure, we're gonna work with every single other radio quiet AGN. But so I'm gonna show you a little bit later the other sample. But here what I show is that at least for scales of smaller than 10 per sec, for 1068, you have a magnetically dominated AGN torus that is helping the accretion flow onto the supermassive black hole. So parallel to these AGN observations, we did a very small pilot study of radio quiet and radio loud AGN using SOFIA. So in this case, what I show here is the same picture as I showed before for 1060 and Centaurus A, but I'm gonna focus in the central 1 kilo per sec. So here I show the white lines that you see on top is the B field orientation of the the B field orientation from magnetic aligning gas grains in 89 microns. And what I see here for 1068, you have an unpolarized core, so the polarization is smaller than 0.4% at scales of 100 or 200 per sec. And Centaurus A, you have a polarized core of 7% or 7% of polarization at scales of 50 per sec. So basically, in this, at least in this one-to-one comparison, you already see a very low polarized core for radio quiet AGN, a very highly polarized core for radio loud AGN. So in order to understand this, we need to go and compute the total spectral energy distribution and study where the total emission comes from first. And then once we know that, we know the physical mechanism of the polarization measurement. So in this case, what I show here is the 5 micron to 1000, more or less to radio to 5 gigahertz total ECD. So here on the top, and you see the measurements of Herschel on orange. The stars are the Sophia, and you have the Spitzer in red for all of them. You see the radio, the typical radio emission from synchrotron. I mean, you see the synchrotron emission on radio, and you see the infrared bump that we estimate to be dominated by dust emission in the central region with this with a characteristic temperature of 20 to 30 Kelvin. This is for the total intensity. So we know that this infrared bump, let's say, so it does emission from some structure in the center, and then the polarized ACD are these stars and the squares on the bottom. So for 1068, we only have upper limits. So these are basically 0.4% polarization. You see the factor here of 100 or more going lower. And then the Centaurus A is 7% polarization. You see that our black body function that we show here, we scale it by the degree of polarization. So basically, it's just like the total flux multiplied by the polarization degree, and then you scale it, and you have exactly the same shape as the total flux ACD. So basically, like the total, the polarized flux is also rising from dust emission, by this case from dust emission from magnetic line dust grains. The synchrotron emission need to break down at some point I don't know, 1,000 microns or so. And this breakdown is coming from the unpolarized core in millimeter. So this point, what I showed you here is that the core of Centaurus A is unpolarized at 1,000 micron. And that's a very strong constraint on the synchrotron emission. So, and this is the synchrotron emission from the core of 1068, and this sorry, of Centaurus A, and on the left is for the synchrotron emission from 1068. So we did this for 9 different AGN. It's the same one, so it's the same kind of styles. You see the typical suspects on radio-loud, radio-quiet AGN, Circino, Centaurus, 4151, and so on. So we have a 4151 as a sample control for type 1 AGN. So you see that you don't have the black body emission, the infrared bump at 100 microns. You may have several gradient of temperature going there because you have an ionization cone in 4151 that doesn't produce this infrared bump. It's kind of like more flat, but still you have a unpolarized core, and the only one that you have polarized emission from are the radio-loud AGN. So you have Centaurus A around 7% of polarization, and you have Cygnus A and PKS at around 10 to 11% of polarization in the core. And then you have the radio-quiet AGN, all upper limits, and the upper limits are lower than 1% of polarization. You have a factor of 5 at least difference between the polarization of radio-loud and the radio-quiet AGN. So you have to think here that that I show in the next slide is that the beam of Sophia is huge. So, and also we are here comparing observations from Circinus, which is very close to PKS, which is a redshift of 0.12. So the polarization is something beautiful because the polarization, you only measure polarization from the structure that's polarized within the beam. So it doesn't really matter how big the beam you have, that the polarization fraction is coming from whatever is polarized within the beam. So in this case, we know from observations of galaxies, also observed with Sophia, that have been resolved galaxies from we have like 20 galaxies resolved from up to 10 kiloparsec with a beam of average beam of 300 parsec. So what we have is that when you integrate the host galaxy, let's say that you have a resolved galaxy, a spiral galaxy face on, and then you assume that the beam is the same size as the host galaxy, and you measure the degree of polarization from it. The median degree of polarization from a spiral galaxy is always lower than 3% of polarization at 89 microns. That means that the host galaxy will not contribute to the degree of polarization that we measure from radio-loud AGN. So this 5 to 11% of polarization, independently, we have PKS and all the galaxies inside of our beam. The host galaxy is going to contribute at maximum 1% or 2%. So this 5 or 11% of polarization need to come from something that is highly compact and with a very strong and orderly field in the center of the AGN. And that the proof of that is Centaurus A. Centaurus A, we had to resolve the host galaxy, and that I showed before. The maximum polarization in the host galaxy is 2%. And the center of the galaxy, the AGN, where the AGN is located, is 7% polarized. So that's the example of like a resolved field and resolved. And Circinus is the other example. Circinus is also very close by AGN. The host galaxy is resolved. The degree of polarization is around 1 to 2%, and the core is unpolarized. 0.4%. So you have the other extreme. So even though you have a highly polarized host galaxy, the AGN, because it's a radio-quiet AGN, is unpolarized. And Centaurus A had the same polarization as Circinus, but you have a highly polarized B field. So whatever we measure independently of the distance of the galaxy is coming from the AGN. So this radio-loud AGN, so we can make a geometrical study and see where the B field of this central engine is with respect to the radio jet. And for Centaurus A, Cygnus A, PKS, you see that the blue line, which is correspond to the B field orientation, is more or less perpendicular to the radio jet. Well, perpendicular, highly offset from the radio jet. Is the 60, 70 degrees offset from the radio jet. Not really perpendicular, but so the AGN and accretion disk are always some kind of like some anisotropy between the radio jet and the orientation. You may have some warp disk, or Centaurus A, you have a warp spiral B field. So so a spiral galaxy too that create this difference between the radio jet and the measured B field. So, and the money plot is this far-infrared polarization with respect to the radio loudness. So we see a clear difference between both of them. So what we did is like estimate compare the far-infrared polarization in the vertical axis with the radioluminosity. We didn't find anything. The reason for doing this is like, well, you may have a synchrotron emission still going on there. So we wanted to check if the radio polarization was coming from synchrotron emission. Is nothing from mean infrared luminosity. So you see it's no correlation neither. So we use the mean infrared luminosity as a proxy of the BBB, blue bump. Oh my God, yes, BBB. I don't and then the radio loudness is where it gives you the ratio between how much power you have in the radio jet with comparison of the mean infrared luminosity as a proxy of the BBB, right? So here you see the unpolarized radio quiet AGN, exactly, blue band, yes, exactly. Thank you, Stephanie. I got stuck. So here what you have is like the polarized radio loud AGN, and then you have a clear division between the unpolarized, the radio loud AGN and radio quiet AGN, which are unpolarized. We have this outsider 1275. So the reason of this one is like it's unclear where the far infrared polarization come from, because the only source that is not a point source. It has some kind of like extended emission, and the extended emission is co-spatial with one of the filaments that you see in H alpha. So perhaps the polarization that we see is from some magnetized filament at kiloparsec scale, which will be very interesting to really actually go and do infrared polarization in the 2 microns to really see that. But the Sophia extended emission in the east side is also being observed by JCMT, H alpha, X-rays, and the B field is, as I show here, intensity A is some kind of like along some filament that is around in this direction too. So, and the only one that you see that like is not really highly offset from the radio yet. So I don't know if, so this is inconclusive at this point in this case, but we have a very clear 3 cases here for radio loud and a few of them here on radio quiet AGN. So just come back to the picture between multi-scale. So now what you have is radio loud AGN, highly polarized at a distance of 100 parsec scales, and then you have a radio quiet AGN unpolarized at 89 microns. The 89 microns is coming from coal dust in the outer layers of the torus, or I mean, outer layers is a matter of semantics, right? So this a region between the connection of the host galaxy with the AGN, and you have the radio quiet are polarized right at the inner edge of the torus up to scale of 10 parsec. So you actually now have a connection between 3 orders of magnitude of B fields, from 3 kiloparsec scales all the way to 1 kiloparsec scales, and you have a pure dynamical structure of the MHD going from galactic scales to AGN scales. Okay, I think I have a few more minutes, right? Yeah, awesome. So I think now what I want to put here is like the most speculative part of the talk. So I give you empirical data or measurements, and now like, is there any theory that we can explain this? Which theory is there, and how can we connect with what we know from the HD point of view of the creation, formation, and evolution of the torus? So I think what we wanted to show here is that we need to go towards a hydromagnetic torus. So here the definition of torus is just a particular region on some inflow or outflow where the dust that is located in an optically thick region that is highly influenced by the diffuse fields as well as the radiation pressure of the active nuclei. So what we need to have is some kind of like connection between the radiative drive fountain model that's being pushed forward by all the observation that we have from molecular light emission and interferometric observations, etc., where you have this polar dust supposedly coming from a radiative driving wind that may be falling down, basically like feeding back the AGN of the host galaxy. And on the other side, what you have is a MHD driving model. So here what I show is a map of this beta plasma parameter. Basically, it's like if the beta plasma is larger than well, this is logarithmic, so it's larger than 0. So you are dominated by HD, so by some radiative transfer, for example. And if you are lower than 0, you're dominated by B field. So if we put this in context of some of the observation that we have seen in the past few years, so you have that this a very beautiful image of Matisse that observed the thermal emission from the base of this outflow going into parsec from superparsec scale to parsec scales are actually in the region of a high plasma beta. So basically what you have is radiation pressure dominated wind at the top of the midplane of the galaxy, of the midplane of the torus. So this is basically what you have is a high plasma beta, yes, radiative transfer, radiative pressure, winds pushing all the matter away from the center. On the other side, in the midplane, what you have is a low plasma beta. So what you have is a magnetically pressure dominated accretion disk. And here in this case, what you have is a dominated toroidal B field. The MHD models of WADA and company predict this B field, toroidal B field of a 0.5 to around 0.5 milligauss, which are actually right on the spot of our B field estimations of 1068, which were more or less at the same time as these observations were out. So we didn't talk to each other. So it was all come together close. So what you have from the ALMA observation, you have that you have a toroidal B field in the midplane of the quadrilateral plane of the torus with low plasma beta dominated by B field. And the Matisse observations are telling you that the outflows itself in the parsec scale in the polar axis are radiation pressure dominated dust. So you actually have some kind of like connection between HD an MHD model going on here. This is one idea. Then you talk with Roger Blanford and then tell you this all MHD winds, and they say, okay, I don't know where the MHD winds come from, but it can be that too. So you may have some kind of like MHD wind very close to the midplane that creates this toroidal B field by differential rotation at some distance from the center of the AGN. Or what you can have also, if because you have very powerful jets, so moving, so with a B field, they're going straight up of the jet. If you have the B field going out, that means that you have an inward electric current, and that inward electric current create a toroidal B field in the plane of the galaxy, which may that the observation that we see from Sophia, it may be a consequence of the jet and not the cause of the jet itself. That you see is more, it's a lot of speculative. We need we need a theory that tell us some predictive observations here. I think just to finish, so for two directions here, I think that we have several observations coming out. So with the 1060A and Circinus. So again, that continued polarization with very high angular resolution, just to resolve the superparsec scale of the B field in the torus. But that continuum only gives you the B field orientation on the plane of the sky. You don't have the direction, so you only have the orientation, and you don't have the information around the line of sight. So what we did was to, well, we brought a proposal that was accepted this year to estimate the B field from water masers. So water maser is going to give you exactly the position of the orientation along the line of sight and strength of the B field as a function of the position across the disk. So, and Circinus has a lot of water masers, so that I show here. They're very bright, and they all trace the disk, the warp disk of the galaxy, the warp disk of the accretion disk, and some of them are in the outflow too. So that actually you can trace you can do a tomography, a 3D tomography of the B field, and strength and orientation that gives you if the B field is rotating, is going inward, going outward, and also a B field orientation as a function, B field strength as a function of the distance too, and as well as in the outflow too. So this is for going really in detail of the in the AGN, but to do a full sample of radio quiet and radio loud AGN, you can do B field observations of gravitational lens galaxy at redshift. And the proof of concept was this arm observation from last year of a gravitational lens galaxy. So this is a dusty galaxy at redshift 2.6. And these are actual observations with ALMA, with that continued polarization of 0.5 arc-second, which correspond to around 400 parsec at the source plane at redshift 2.6. And you see that the degree of polarization is very high, around 2% of polarization, and the B field is parallel to the plane of the galaxy in this case. So that actually is telling you that you have a very strong large scale B field very early in the universe. So you already are very highly amplified B fields in this case. So yeah, so I think that I'm just gonna end with the big picture of multi-scale B field in AGN, saying that we really need to start thinking about the AGN. So sorry, the AGN triad, yes, as a MHD dynamical structure that connects the host galaxy with the accretion disk, helping feeding the AGN with the supermassive hole, but also this MHD is the mechanism that produce the winds that we observe at hundreds of parsec scales created by that are generated due to the accretion disks that are magnetically dominated. So I think that I will end here, and if you have any questions, so we can discuss about all this. Thanks.
Great. Thank you, Enrique, for that lovely talk. We definitely have some time for some questions, so you can either type in the chat and I'll read your question if you would rather not talk, or you can feel free to unmute yourself and ask your question as well.
Okay, I could start.
Okay, great.
Was any of the AGNs you looked at were Compton-thick nuclei?
Compton thick. I mean, Circino is Compton thick, right?
It is? Okay. Because that'd
yeah.
be influenced with the lot of dust there than normal, a lot of dust inside the, particularly in the center than the normal AGN.
Yeah, yeah. So yeah, and yes. Well, we see these objects here. I think Circino may be one of them. I don't know if 1060. I don't know that. It should be.
Oh.
Yeah.
Yeah, I mean, one AGN which I'm studying is NGC 3281, which is Compton thick. There's already a model of the torus from mid-infrared and X-ray, so that'd be interesting to compare what you found to what the model's there.
Yeah. Is that object in the south?
Yeah.
I don't know. Okay.
Oh, yeah. Minus 30 deck, I think.
Okay, perfect. ALMA. Then for ALMA will be great. Now that we don't have Sophia, we need to rely on ALMA.
Yeah, so that brings up a question that I had, Enrique, which is, how does the loss of Sophia going to affect these kinds of studies moving forward?
Yeah, so I think this is the future direction I was saying. I think that we can do the same as we were doing with Sophia, but going to higher redshift. Basically, a redshift 2, 3, 4. You basically are in the far infrared bumps. So in the infrared bump that we see in these galaxies in the nearby. So, and we have a bunch of radio loud objects, radio loud objects in at high redshift. So we can do these observations and a lot of them with ALMA. And the proof of concept is here, is this one. So we can actually observe it. And the other good thing is like ALMA, this is only 0.5 arc-second. So if they are bright enough, we can go to 100 parsec scales easily for a redshift 3 or 4, in this case for some of them. So in order to make a sample, a larger sample, yeah, we can do maybe 10, 15 of them with ALMA in the next few years. Mm-hmm.
I have a comment or a question, if I might.
Yeah, of course.
Yes, it's very interesting to sample and map the magnetic field. It's the big unknown many times, and I think it does not. I get the idea, and what you say that apparently from the galaxy the magnetic field is not that important. As compared with what it comes from the central region. I would say that in this whole picture, I don't really see much the point of connecting with the torus itself, because precisely on the samples you have put it here in this biograph, Centaurus say so far we don't see any torus at subparsec scale, and 1097 neither, and it's a full jet emission. The spectral distribution is a parsec scale, a few jet emission from radio to the high energies, like Centaurus say. So it's normal you see a polarized emission. The same with M87. There is no torus at parsec scale so far.
So where the occlusion in 1097 and Centaurus A come from then?
The nucleus of there is dust, but not a torus. We have not seen a torus.
Yeah, so I think the idea here is like never say there's a torus. It's some dust structure helping the accretion onto supermassive black hole, right?
Okay,
So
yeah, it's a very different thing to say there is a particular structure. What I'm saying is that there is definitely oscuration, but when you go to parsec scale, you isolate the nucleus, the core, and this core is pure jet emission. That's what I'm saying. A parsec scale 43, M87, Centaurus 8, and 90, and others. Of course, I would expect polarization there from the jet. There are other cases that are jet emission and we do not see polarized. For example, I would encourage you to see an object like the NGC 1052. It's the same, but we do not see polarized. This is very cool.
1052, you say?
Yes, 1052.
1052 is polarized at 10 microns, actually.
We make observations. We didn't
Yes.
see polarized in other spectral regions we were looking at, and it's a pure jet emission. We are seeing now as well with the GMWST.
So then, I mean, we see on all these infrared bump, the 100 microns. I think this is what happened here, right? So on this this infrared bump is dominated by dust, no by
No, there are no infrared bumps. Is what I'm trying to say, because if you see a large scale with large beams, yes, you see an infrared bump. But when you isolate the core, I'm saying a parsec scales. And now we are conforming us as well with GMWST. It's a pure jet emission. It's a power law, if you want, power law. So I do not see much the connection. What I see interesting is that in the radio quiet, in some cases you see not much polarized. And for example, Tyrtinus have a very large radio structure and an incipient core, a bit of jet emission, which is still not resolved. And it's quite surprising we do not see polarized. So there are objects that we see a jet and or incipient jet or like a 4151 that you mentioned too. And the polarization is not much, maybe because there's a lot of intervening material in the view and then gets unpolarized. So it's a little bit complex. But
so then the 100 microns, if it's not, that's where the 100 microns come from. It's not synchrotron. So so it's not, so the 89 microns polarization that we observed with Sophia, and also in 10 microns too, we observe a highly polarized radio loud AGN with signal state, for example, is one example that is obscure, you know, with this dust there. Call it torus, call it whatever it is that obscuring structure, dusty and molecular obscuring structure. Tens of parsec scales. Those are coming from thermal emission, not from
maybe
thermal emission.
I'm not discussing about that, but I'm saying that these specific cases that you mentioned, we are studying a parsec, the whole spectral distribution from radio all the way to high energies. And it's a power law with the high energies, the quantized component of this synchrotron emission, the jet. So there is no there is no free parameters to get.
So
now you measure in larger apertures, maybe of course you polarize emission. Definitely my camp has from non-thermal, but I was just wondering where it might come from. I'm saying that the center is non-thermal.
Yeah, I think the radius here is what I show here. So this infrared bump is coming from a structure that is like 5 to 100 parsec scale. So, and that is, yes, there's dust there that's producing the obscuration to these AGNs, for sure.
Yeah, there are plenty of filaments there.
Exactly. So then that's exactly where we are getting. So it's a dust structure, the 5 to 100 parsec that is magnetically dominated and influenced by the AGN. It's not in the Lyosite. It's not in the host galaxy, because the host galaxy is unpolarized.
Is there time for another question?
Yeah, we have time for maybe 2 more questions. Yeah.
I mean, I've been saying, speaking a lot, if anyone else, so I was going to say, there are some safe grids which are radio intermediate that they're a bit more radio loud than your typical your classical one, and not quite like radio loud like a Centaurus A. I'd be just curious to see how they relate if they're in between.
Yeah, Yeah, that will be. We need to make a larger sample for sure, and more type of AGNs and more different environments. We got the pilot study. We have like 20 AGNs that we wanted to do, but we only got 9 before it was canceled. So what we got at this point.
Nearby one is NGC 7213.
Yeah.
Okay, last question, maybe from someone who hasn't had a chance to ask any questions yet. Any students, for example?
Misty?
Yeah,
I'm sorry, I didn't find the hand, to ask. So I have a question.
sure, go right ahead, yes.
Okay, thank you. Well, thank you, Enrique, for the really nice talk. It's so interesting. And I was wondering if you can measure the size of this region because the magnetism, because you are in the really core of the AGN, and you find unpolarized or polarized that depend of if you are radio quiet or radio loud. So my question is, if we think that is the torus, this dust, we can measure with magnetism the size of this region, because even if we have some information, we are not, until now, we don't have exactly what is the size of the torus, the VLR, the region inside of. So do you think that it is possible with this, we can apply this for that?
Yeah, I mean, I agree. I mean, we don't know. That's the reason why I always say, like, this interface, I mean, this matter of semantics, right, between the larger scale, I mean, the outer part of the dusty structure obscuring the AGN. I think the size that I got is from pure black body point of view, right? So you have a modified black body function here. You can estimate the mass, and assuming equilibrium, thermal equilibrium, you can make a rough estimation of the maximum distance at which you get this dust temperature at this mass, and then you get this radius of the dust for optically thick dust of around 5 to 120 parsec scales. So something between, yeah, up to 100 parsec scale. So you have some structure that is magnetically dominated around the AGN, whatever that structure is.
Okay, thank you.
Mm-hmm.
Well, thank you again, Enrique. I think I'm going to stop the questions there and stop the recording. But certainly, I think, Enrique, you're probably available by email if people have follow-up questions. I just want to thank everybody again for joining us for this final talk of the calendar year, actually. And we will be in contact with plans for spring, in your email inboxes, so keep an eye out for that. And thank you, everyone, and thank you again, Enrique. It was an excellent talk.